All right, continuing. We've already seen that if you do an unweighted least squares regression, we get the results from Linus, right? So this is your slope, and that's your uncertainty in your slope for Linus, and you got slope and uncertainty in slope using the weighted regression template that we're creating. And this is your y-intercept, and this is the uncertainty in the y-intercept. Okay, and we've seen that chi-square is this bottom right corner of the Linus output. And before you've learned, when you talked about Linus before, you've learned that this number right here, just below the uncertainty in the slope, that's actually the, what's called the correlation square of the correlation coefficient, r squared, okay? So we can calculate that as well, okay? And so let's see, what else do we need to do? Oh, okay. Um, let's see what we have so far. If we let's pretend that our uncertainty and our y values are 5. We assume they're all 5. They're all 1, right? Let's assume they're all 5. And let's see what happens. So if we make our weights all 5, they have the same weights, right? They all have, but their weights are all 0.04. Oops, undo. The weights are all 0.04 because 1 over 5 squared, 1 over 25 is 0.04. Notice you're still going to have the same slope, okay? And the same y-intercept because it's still equal weights, okay? And you still have the same uncertainty in the slope and uncertainty in the y-intercept, okay? Because again, like I said, they're equal weights. But your chi-square is different now. It's 0.497 versus 12.42 because your weights are not 1. Your weights are 0.04. But let's see what else we can calculate with this. So this is a way for you to, this screenshot in the handout. So a quick way for you to check whether your numbers are correct, okay? You're getting the right numbers. All right. So let's see what happens now if our delta y for the last data point is 15. So let's make the uncertainty in our last data point bigger, okay? So, oh, one other thing you'll notice about this chart right here, you'll notice it has these error bars right here, okay? So that's basically plus or minus the uncertainty. So this is plus or minus 5. So this is 172.8 plus 5, and then down there 172.8 minus 5. So this 172.8 right there in the middle. Okay, so let's make that error bar, let's say for this fourth data point, instead of plus or minus 5, let's make that error bar bigger. So this error bar is going to get bigger right here at 80. So if I change that to 15, look what happens. See, you can see your error bar here at 80 has gotten bigger. Okay, and then you'll notice that now the best fit line goes through, gives more priority to the first 3 data points. There's more weight given to the first 3 data points than to the last data point. So the best fit line actually moves away from the last data point. Okay, and you'll also notice if you did that, that your slope is no longer 0.7089, it's 0.756 instead of 0.7089. The best fit line has gotten steeper because less weight is given to that last data point. All right, so you can see that the idea of weighting does work here. Okay, so this, by making, if you have a larger uncertainty in your y value for a given data point, that should be less reliable than the other data points. So now the best fit line is largely determined by these first 3 data points, which have bigger weights compared to the fourth data point at 80. Okay. All right. So let's see. Let's change all the data points back to 1, the delta y back to 1. And you should find that our chi-square should now agree with the linest output, with the chi-square, okay? Notice your chi, everything's the same except for chi-square, which don't agree because the weight data, the weights are not 1. So if I put my delta y equal to 1 for everything, equal weights for everything, you now get agreement between the chi-square and and for the weighted regression and the chi-square for the linest unweighted regression. Okay. Did I remember to record this one? Yeah, I did. I keep forgetting if I did. All right. So what else do we need to do? We can calculate the what's called the Pearson correlation coefficient, the square of it, so R squared, and the standard error of regression, S of R. Okay, these are two ways that we can assess the goodness of it, how well the line fits the data. But these really should only be used when you're doing unweighted least square. So you don't need, if you really need this information, just do a line nest. Okay, and so these are but so you, um so you can do that calculation. For us to be able to do that, we need to first calculate SYY, the centered product sum of the difference of y from the mean. Okay, so SYY, just like SXX, but instead of here, you're using y values. Let's put that in row 24. That is SYY. So this is going to be equal to sum product, open parenthesis, we need the weights, comma, and then open parenthesis, y values. Okay, so B4 to B7 minus the average y mean. Let's make that an absolute reference to B15, the mean y, close parenthesis, caret 2 to square it. That would be your SYY. That is called your that's what Excel calls SS total. Okay, 1017. 1017, okay, 0.506. So we calculate that first. That's the sum of the squares of the difference between individual y values and the average of the y values. So now we calculate what's called the regression sum of squares, SSReg, in row 25. That's just the difference of SS total, which is SYY, minus the chi-square. Okay? So let's go ahead and do that. This is going to be equal to SYY minus chi-square. And that should be 1005 for the data that we have here. And you can compare that to what you have in the handout. So we're doing it right. Okay. Now the ratio of SS reg to SS total, so SS reg over SYY, that's going to be the square of our Pearson correlation coefficient. Row 26. So this is going to be equal to SS reg, sum of squares of regression, divided by SYY. Okay. So SS reg, okay, that's a standard error of regression, S of R. Okay, so it's so 1005 divided by 1017, that gives you 0.987. That's the square of the correlation coefficient. That's what we're getting here, 0.9877. So that's your R squared. This is the same as this number right here. Okay. So we are reproducing the numbers that the linest function gives us from Excel. Degrees of freedom is just n minus 2. So um, let's calculate. We're going to need that to calculate the square root, the last item here, the square root of SS residual over degrees of freedom, which is the standard error of regression. Okay. Um, that's SEY. So degrees of freedom, this is equal to n, this n right here, minus 2. Okay, so the formula here is number of data points minus 2. And then SEY, this is just the square root of SS residual. That's the sum squares of residual. The square root of chi-square divided by the degrees of freedom, which is this number right here. And then that's SEY. So that 2.49, this one right here is your 2.49 SEY. That's called SEY. Okay. That is the standard error of regression. That's what Excel calls it, SEY. Okay. The standard error of the, I'm sorry, the standard error, yeah, of regression, also known as a standard error of the Y estimate. That's what Excel calls it, SEY. It's also known as a standard error of regression, S of R. So this is the square root of the ratio of chi-squared to degrees of freedom. This basically tells you on average how far the Y values are from the experimental values. In the same way, the standard deviation tells you on average how far individual values are from the mean. So in the Linus output, where do you find this? This is going to be found in below the uncertainty in the y-intercept. So this is correlation coefficient, standard error of y estimate, or standard error of regression. This 12.42 is chi-square, okay? 2 here is degrees of freedom. All right. So that is how you do weighted linear regression. And then you can play with the weights here depending on your uncertainties. And then you should be able, this chart right here uh, automatically adjusts for you. Now, if you don't go from 0 to 100, you're gonna have to change this number right here. So let's say I only want to go from 10 to 90. I can just change this 10 to 90, and you'll notice it only goes from 10 to 90. But if I want to extend this to maybe 150, you'll notice that this doesn't go past 100. I have to change this scale right here. I have to change the maximum to 150 so I can see it. Okay. Now it goes to 150. Now my Y is 264 at 150. So this only goes to 250. So I probably want to increase this to maybe 300. Okay. So you're gonna have to do some manipulation of your axis to be able to see it on the chart. The chart is pretty much almost automated complete, except for the fact that you have to put the right scale in. So you have to look at your net numbers here. It's a good range of numbers to use would be some nice round number just below the lowest X value here, and some nice round number just above the X value here. So I'm going to use 100 there. And so now I can change this one. I want to go from 0 to 100. And I'm only going 170, 150, 170 to 220. I can 150 to 250 right there. Okay. So that's it. for this lesson on linear regression. Now, for your homework, okay, this is where you have to review how to propagate errors from last semester's lesson. So let's say question number one, let's say your y values are obtained from experimental values of p, and your y is actually 1 over p, okay? So p is experimentally determined. So you know the uncertainties in p. How are you going to calculate the uncertainties in 1 over p? That would be the uncertainty in your y. So if your y is equal to 1 over p, you know delta p and you know the p, how are you going to calculate 1 over p? So what's going to be the formula of y? And then what will be the formula for the weights? Same thing. These are the two most common uh, transformations you would do for your data to make it fit a straight line. The second one is when you, instead of some signal s, you take the natural logarithm of that as your y value. So if you know the uncertainty in s, how do you calculate the uncertainty in y if y is ln of s? So you need to submit the answers to that. And then you're going to do this right here. You have data for, actually this is for Boyle's law. This would be very similar to the data you'll collect for your first experiment. So you have, you vary the volume of a gas contained in a syringe, and then you measure the pressure of the gas as you change the volume. So as the volume expands, okay, the pressure changes. Now the actual volume here is V naught plus the syringe reading, where V naught is some unknown initial volume, okay, and then PV equals nRT is the equation that describes the behavior of the gas at sufficiently low pressure, and these are sufficiently low pressures. So you substitute V naught plus X for PV right here, and I want you to show that if you are to actually plot 1 over P versus X, you're going to get a straight line. What would be the slope and what would be the y-intercept? Okay, and then you have to do weighted regression because your y is not p, your y is actually 1 over p. Okay, so what would be the uncertainty in y over p? That would be your delta y. So for your homework, right here for your lab report, I need the answer to homework questions 1, 2, and 3 in the handout. And then I want you to submit the Excel document to support your answer to question 3 in the handout. And that's it. That would be due a week from now.